Good morning, everyone. Can you all hear me?
Yes, and we can see the using energy PowerPoint.
Good, thank you. Kate, can you meet me in school today by 1 o'clock? Hello?
No, I have another class at that time.
Oh, okay. Okay, so let's look at what we have today. So this week we'll be looking at the chapter 11 of our test, and we'll have by next week look at 12, and hopefully the last week before exams we'll look at the last chapter, which is chapter 13. Okay, so we'll try and go fast. I didn't post any assignment for the last chapter, but I expect us to look at those examples that I said you should study in the test. Please just take that like your assignment. Look at each of the examples, study them. It's important that we do so, okay? So today we are looking at using energy. The immediate previous chapter talked about work and energy. And in the last chapter, we just established one equation that we kept using to solve problems. And we call that energy, work energy equation. And that same equation is also going to be useful to us in this chapter, but we'll be looking at them in terms of how we apply the energy that we know. We already know their forms in the previous chapter, okay? So we'll be looking at how that we can use energy in our body. We'll learn how to calculate how much energy our body requires to complete a range of tasks, okay? We'll also see that, understand by that, how energies that are transformed from one form to another can be measured or calculated. We'll also be looking at the relationship between temperature and heat. We will learn how that heat is the energy transferred due to temperature difference from objects. We should be able to get to that today. And then later in the chapter, we'll look at the heat engine and how to calculate the conversion from thermal energy to work, okay? Our general goal will be to learn about the practical energy transformation and the transfer, and also look at the limits or the limitation of the efficiency of the energy system. And we will do that with some basic simple calculations, okay? So we'll begin the discussion of our using energy with the very first topic, which is transforming energy. So when we use the word using energy, we simply mean that we are transforming energy from one form to another. For example, when you eat, the chemical energy of the food is transformed into kinetic energy that your body uses to do or perform a range of tasks or move. Okay, so we'll look at quickly an example of energy transformation before us. We'll see this is a solar light. At the top, we have solar cells. During the day or light time, it absorbs energy, convert it to electrical energy, and store the energy in the battery in form of chemical energy. Then this is transformed later at night to light also. So the chemical energy, you see the chemical energy in the battery being converted back to electrical energy, and it gives us the light energy, or emits light through the emitting diode. So we see that the energy that came in as light energy from the sun was converted, stored, and also gave light in the end, gave the light energy. We also see another process. The light energy from the sun is absorbed through photosynthesis by the pigment of the soybean plant. And the energy created is concentrated as chemical energy and stored. Now, from that soybean that was harvested, the oil, which is from the chemical energy absorbed from the sun, is used to make candles. Okay, and then the candles are later burned, which then converts back the chemical energy and transform it into the light energy as well. And also the thermal energy is given off to the environment. Now, we noticed something about these two examples before us, which is also a common scenario to the general conversion processes, that the same energy that was at the beginning is what was given off at the end. Okay, when I mean by the same energy, I'm not talking about quantifying it right now. I'm talking about, okay, we got light energy and we gave out light energy in the end. Okay, so it went through several processes and convert back to its original type of energy. So if we recall from chapter 10, we said the work energy equation is simply change in energy being equal to work. And change in energy is the total sum of the different energies in the system. Okay, now we know that it's systems that allow the exchange between its environment, that is a non-isolated system, is the one that will have change in energy reading equal to work. But for an isolated system, remember, W is always equal to 0. So change in energy will be equal to 0. Okay, so keep this in mind because we have looked at it in our last class. So recalling that change in energy is equal to work, it means that whenever we have a system where there are changes in energy, we can actually describe it in terms of its work or heat when the system is not isolated. Okay, so this equation is also what we use to understand energy transfer. And the energy transfer can either be positive or negative. And when are they positive? They are positive when the system is gaining energy, and negative when the system is giving off energy. Okay, so if a system gains energy or energy is transferred into it, it's positive. But when it gives out energy, energy is transferred out, it is negative. Okay, so let's quickly look at an example of a system for energy transformation on a pump storage system. Okay, so we'll have, in the first case, electric energy that helps to pump this water uphill. It goes up, so the water goes up, and the energy input is 100 joules. Now, 100 joules, as the water is going up, we know that thermal energy is released whenever we have any system, fluid, drag, or surface contacts. Those are some of the contact energies that leads to the release of thermal energy. Okay, so as water pumps up the hill, 25 joules is, let me use the word lost, but we know that we don't really lose energy because they are transformed to another form. So it's transformed, or let's just borrow the language lost, to thermal energy. Okay, so in the end, when the water gets to the reservoir, it's just 75 joules that will be inside. That's the energy, potential energy of that water in the reservoir. So it is less than the energy input or stored in the system. Okay, so when the water is pumped back down, we see also the 25% loss to thermal energy process. So in the end, only half of the original electric energy is being recovered. So we see that we put in 100 and we got 50. So the idea of quantifying the energy we put in and the result it yields is what brings about the efficiency determination for a system or a process. Okay, so therefore we'll look at efficiency to better understand how we use energy, because whenever we are using energy, that is transforming energy from one form to another, we also expect a result which many times does not equate the effort put in, all right, or the energy put in. So that's what efficiency is, what we use to describe that. So what is efficiency? We use letter E to represent efficiency. And efficiency is simply equal to what you get, that is the output, over what you pay, that is the input. Okay. Generally, the larger the energy losses in the system, the lower its efficiency. Okay. So if we assume that for the previous system we just saw, we're not losing up to 25% energy to thermal energy, we will see that the efficiency at the end will not just be half, it will be more than half of what we put in. Okay. Also, we'll have two different sources that reduces the efficiency of a system. Okay. One of which is what we call the process limitations. And the second is the fundamental limitations. Now, the process limitation talks about the energy transformation process that is due to the design of the system. Okay, so the pump design that we saw earlier can actually be made such that the thermal energy, or if we better insulate the process, the thermal energy given off to the environment will be less than 25. Okay, so the process limitation is dependent on design, while the fundamental limitation is dependent on physical laws, something you really cannot change. You cannot change so much or circumvent around them. But it is the fundamental limitations that theoretically inform our designs to optimize efficiency. Okay, so from these two limitations of efficiency, scientists use it to improve or better their designs. all right? And we also stated in the last class that it is actually difficult to measure directly the thermal energy, that is knowing distinctly the initial and final. And that is why we could not express change in thermal energy in terms of initial and final expression. So we just say change in thermal energy. In this chapter, we'll understand the reason why, okay? Because when we describe a process, we're able to put in a quantity of energy. We'll bring out, we know the quantity that we got out. We know that the ones we cannot measure are given off to thermal energy. And that is how we're able to measure the change, okay, in the thermal energy. For the process of pumping upward, what we got at the end was 75. So we know 25 was given off to thermal. When we were going down, we got 50. We know 25 again was given off to thermal. So that's how we determine or measure our thermal energy. So let's look at another transformation process, looking at the energy transformation in the coal-fired power plant. Now, if we look closely at this power plant, we see the water in the tank here increasing its kinetic energy, that is supplying thermal energy into the system, which is 100 joules, was supplied into the system. It heats up the water, give out steam that was sent into the turbine to turn the turbine, okay? So 100 joules of steam was sent, or energy from the steam was sent into the turbine, which turns the turbine, and then the output was 40 joules. From the output we got, we know that 60 joules has gone to thermal energy, or is exhausted into the environment. And that is why sometimes you use the word loss. We've lost 60 joules of energy. So to calculate the efficiency of that system, remember, efficiency is what you get, which is the 40, over what you put in, what you paid, which is the 100. So this system is operating at 40% efficiency, okay? So our result is 0.40, which is 40% multiplied by 100, okay? So it's operating at 40% efficiency. So let's quickly look at the strategy that we'll use to solve efficiency problems, okay? Efficiency in this term is referring to energy efficiencies. Now, the formula for efficiency we are using is the general formula for efficiency that we know worldwide. Tells you what you put in over what you put out, times 100 if you want to express it in terms of percentage. All right. So the first approach will be to first determine your output and what your input is. So you start by this, after you determine the output and input from what the question says or description of the process, you'll be able to tell which is the output or input. So you could now, from the information of the output, determine the process of work done, or tell if the system is an isolated one or is interacting with its environment, okay? For example, when you climb a stair, you put in energy from chemical energy conversion from the food you eat to getting to your destination. That is where you have the potential energy. You'll be able to define such a system. Is there work done? If there's no work done, then the system is an isolated system because W is equal to 0. So change in energy will be constant, okay? So you determine also what you pay, which is the input, energy input. Once you've gotten those two parameters, you can then proceed to applying your efficiency equation to solve the problem, okay? Then you check your answers if it's reasonable. There's no way you calculate efficiency and be getting above 100% efficiency, because that means that, okay, yes, it's possible, but not that when you determine an efficiency of a process, you'll now be having above 100%. Okay, usually efficiency tends to stay less than 100%. Now, when we address a case where we have to amplify energy, it's a different scenario from this one. All right. So let's consider an example to buttress the approaches we've just listed. We'll look at the example before us, a 75 watts incandescent bulb and a 15 watts compact fluorescent bulb is shown below. This is the incandescent and this is the compact. Then we're asked to determine the efficiency of these two types of bulb, okay, for converting electric energy into light. Now, we know that 1 watt is also equal to 1 joule per second. So when we say 75 watts, we're actually saying 75 joules per second. So it's direct. So we'll take it the way it's given. For the compact fluorescent bulb, it produced, or both of them produced 3 watts each. So what was put in for the compact is 15, and then it produced 3, which gave us 20% efficiency. Okay, but for the incandescent bulb, we put in 75 joules of energy and we got 3 joules. You see that that bulb is operating at the 4%. It's giving out light quite all right. They both gave out the same energy, light energy, but the efficiency of one was more than the efficiency of other. We put in less energy and we got what is approximately. Okay, I have a hand raised. Can you come on the mic, please?
Yeah, I just wanted to check. So like, cause when it has a better efficiency, that's why like a lot of like people are like switching to fluorescent as opposed to just like the classic incandescent bulbs, because
Yes.
it's like you get more bang for your buck kind of thing.
Yes. So
Okay, cool.
that is why we call this one energy efficient bulbs, because you
Okay.
use up little to get approximately the same results than this one. You're using up, imagine using up 75 joules from your energy system just to get 3 when you can just use 15. That means you can use 75 to get triple what you put in here. Use this one to get 3 times. This one will use 3 times what one of these we use. Okay.
Okay, thanks.
You're welcome. All right. So I'll encourage us to also see or study this example 11.2. So let's move to the second part, which is the energy in our body. Okay, how do we use energy in our body? We already established in our previous class that the energy in our body system is actually chemical energy from the food that we eat. Okay, so we see the figure here. This person eats food, which is converted to chemical energy by the digestive processes. Okay, and then from this chemical energy, we put in work to the environment, and also our body gives off heat as we do work. So the chemical energy in us is transformed to heat, work and heat to the environment. And this is simply the breakdown of the equation process of digestion. For example, the food you eat gets to be decomposed to glucose plus the oxygen you breathe in to give you what you breathe out, then water plus energy used. Okay. This equation is important because this is what informs how we can quantify the energy that we use to do work. Remember, we said we'll learn how to calculate the energy that we actually use to perform variety or range of tasks. Now, we just want to use this example to better explain what we mean by energy used up in our body. The simple biological processes of converting ATP to ADP. ATP is the adenosine triphosphate, is converted to adenosine diphosphate. Adenosine triphosphate is actually the power source for cellular processes. It is the exact energy that we use to do work. But first, it is converted to ADP. It is now recycled from ADP molecules back to the chemical energy and also converted back to ATP, which is the energy that your cells or the body cells needs to do work. Okay, so having understood the conversion processes, we want to then quantify the efficiency or the energy that we use to do work. When you eat, it's not all the energy from the food that is consumed, but some people consume more. Okay, so we have that the metabolizing one molecule of glucose releases 4.7 times 10 raised to power minus 18 joules. If everything goes smoothly in the chemical pathway for the system as described earlier, going from ATP to ADP and then ATP, the metabolizing of one molecule produces 38 molecules of ATP. Okay. Now, we have said in the first case that ATP converting one molecule of ATP to ADP releases this. Okay. And the metabolization process from ADP releases this. And in the end, we got 38 molecules of ATP released to the body to do work. What is the overall efficiency of this energy conversion process? Okay, so first is to, like we said, define your input, then define your output. The output tells us that we'll have 38 molecules of ATP, and the energy released during the conversion process is 5.1 times 10 raised to the power minus 28 joules. So this makes up what we get. And what we have put in is the 4.7. So applying the equation of efficiency, we see that this person that we saw in the first image actually used up 41% of the food they ate. Okay, so the remaining percentage will go somewhere. Some will be converted to thermal energy and some will be stored. So we'll look at also the storage of energy. But before we do that, we have standard calculations that are already established, and then that makes up the table I'll be presenting to us. But what you have noticed is that thermal energy is often measured with the unit calorie. Now, the unit calorie is used in most cases other than joules. But we have two types of calorie. When we say calorie in your food, it's different from the calorie that is just the unit for thermal energy. So to establish quickly the relationship between these two, the one for food is always written with a capital C or represented as C. Okay, while the other one is written with the small CAL. Okay, but this for food is written with capital. Now they have different values. 1 calories, that is one with the small, is equivalent to 4.19 joules. But for the calorie of food, 1 calorie for the food is equal to 1,000 calories. So 1 food calorie is equal to 1,000 calories. That means 1 food calorie will be, just add K here, that's what you have, 1 food calorie is equal to 4.19 kilojoules, while normal calorie for the thermal energy is 4.19 joules. So we have a table here showing us the different energy contained in the several kind of fuel. The one our body uses is the carbohydrate, the one we see in food. The energy associated to that, 1 gram of carbohydrate gives 17 kilojoules of energy. So please, I encourage us to also study that example. So this is also the table. We'll be using some information here to solve the problem example we'll be looking at. So just go through this to note the different energies in the different kind of food that you eat. Okay, so we also have the energy that your body uses when you are resting. The organs of your body is making use of energy from the food you ate. Conversion process is going on, and the body uses minimum of 100 joules to repair the tissues, the organs of your whole body system. Okay, so we'll have what the brain is using, what the liver is using, what the brain is using, and so on. All right, so that brings us to the next one, which is the efficiency of the human body. The human body, most times when we do chores, we actually engage majorly the closed or isolated system, because most of the processes going on is going on within us. So let's take example of this person climbing the stair. The initial position, he started climbing and got to the final position, covered the distance changing Y, as we can see in the diagram. But the system is regarded as a closed system because it's actually climbing the stairs. No work is done on you. All right, it's just changing position. So it changed from potential through to kinetic, then back to potential. And we know that the potential energy that is operational for object above the ground is the gravitational potential energy. So that's why we have the UG here. So the total system there is going to be changing energy equal to 0, which is constant. That means it's an isolated system. Now, we notice something. It's going to be using up chemical energy. All right. So potential energy is increasing and is giving out heat. So these two will be increasing. Therefore, the chemical energy is negative and the potential and thermal is positive because it's using up this one, this and this are gaining in the process. So this is losing, this is gaining, this is gaining. Right? So with that information, we can rewrite this equation. If this one is negative, then it can move or crosses the sign of equality. It becomes chemical energy equal to potential energy due to gravity plus the thermal energy. So that's what we have here in our final output. But we take the magnitude of this process because we will not be having a negative value. Okay. So if we recall that the formula for potential energy is equal to mg change in x, we can actually determine or calculate the efficiency of this human that is climbing the stair. Now, if we make an assumption that the person climbing that stair weighs 68 kg, and he climbed a height of 2.7 meters, we can calculate its gravitational potential in the end, which will be substituting the parameters into the formula given here, we'll have 1,800 joules. All right. So if that is energy output, because it got to the top of the stair, we can actually determine the efficiency. Now, from the previous table we displayed, we saw that the typical energy used to climb a stair is given as 7,200 joules. So if we know that this is our output, this is our input, we can actually determine the efficiency of that system between output over input to have 25%. So it's generally taken to be that the human being efficiency for climbing a stair, or the average human, is 25%. Okay, so this is a generalized or adopted value for climbing a stair. We have generalized adopted values as well for running, for sitting, for resting, and that was how we could determine the energy used up for resting. Okay, so if what we are obtaining or using up is 25%, we already established that some are being stored, and that's what we want to quickly look at. Energy stored. Okay, so energy stored in the system, you have consumed food, you did not use up to 25 to do your chores. Most of the energy will store under the skin or form fat under your skin. So this explains the weight gain. When you eat, you keep eating, you're doing only little tasks, you discover that you start gaining weight. Okay, because fat will start accumulating under your skin and you begin to increase in size. All right, that's simply how the body system stores energy until they are used up. Okay, so let's take quickly an example to understand also how we use up energy and how they are stored. Now, the body stores about 400 grams of carbohydrate. Approximately how far could a 68 kg runner travel on this stored energy? So what is the distance that the 68 kg runner will cover if the person already stored up 400 grams of energy in the system? Okay, I presented a table before, several tables giving us standard values that we did not have to look at one after the other, because I just want to be sure we'll cover what we have today. So I just skip through those tables. But I extracted some of the information there to solving this problem. One of which is that we have that in 1 gram of carbohydrates, which I highlighted in that table, that then we have 17 kilojoules being produced as energy produced by 1 gram of carbohydrate. That means if the person has 400 grams stored up, the chemical energy stored in the system, because the energy from food stored in our system is the chemical energy, right? It's actually 400 grams times, this is expressing 17 kilojoules in joules gram, okay? So 1,000 grams is equal to 1 kilogram, okay? So we have the energy for chemical energy stored in the body system to be 6.8 times 10 raised to the power 6 joules. All right. So we now know from the information supplied in the question, they only supplied the weight of the person and the gram, and we'll have standard values that we can use to interpret the question. One of which is that energy in a gram of carbohydrate. Another one we want to use is the energy for a person running. All right. Remember, we just did an example, which is establish an adaptive value for someone climbing a stair. An adult that will climb a stair will use, on the average, 25% of the energy to climb a stair. So we also have adaptive value for running. An adult will run 15 kilometers per hour and use 1,150 watts, which is 1,150 joules of energy. Okay, so if this is the adaptive value for an adult running, we can actually, from this information, determine the time. Remember the equation power, P equal to a change in energy over power is actually the rate of energy change. Okay, so if we make this the subject of formula, that is how we got this equation here. So we know the chemical energy. We know from this the power rating for running. So the chemical energy and the power over the power gives us this in seconds. When we convert it to hours, we have 1.64 hours. So from the information given and the standard adopted value for range of activity for human, we can actually input this into the equation of velocity to determine the distance, because the person is running at a particular speed, 15 kilometers per hour, and then we already obtained the time from the power equation. That is why we converted to hours so that we can use or express our answers in the same unit. Okay, so we'll have V to be equal to change in distance over change in time. So change in distance, therefore, is equal to V change in time. That's the equation you have here. Okay, so multiplying the velocity or the speed, 15 kilometers per hour, times the time, which is the 1.64 hours, we're able to obtain the distance that that runner will cover using this quantity of energy. Okay, so you see that from the energy information, from the stored energy, that is why when you wake up, you've not taken another meal, you are able to perform certain tasks. Why? Because you have some energy stored up in your system. You can actually reach out and use them up. All right. You see people who try to lose weight, try to take a walk, try to run, try to climb the stair, just to use up those energy stored up under their fat. Okay. So we have several activities, one of which is like taking a walk. We analyze the human locomotion analysis. When you walk, what actually happened? And when you run, what actually happened? We have standard value also for when you're taking a walk and for when you're running or for when you're climbing stairs for different kind of exercises. So let's just look at the plot of the energy diagram of what happens when an adult is taking a walk. We see at the beginning of the stride, the velocity of your foot will increase. Then you lift it up, takes this curve. Okay. So when you're here, you're at the maximum kinetic energy when that is the picture you can see here. The foot is about to take another land. The potential being converted to kinetic and then it's going back to potential. All right. So we see here when you are at the maximum speed, the peak, you're at the peak of the curve. Then at the end, the stride on your foot momentarily, the kinetic energy will be lost and it goes back to rest. That is, the foot is on the floor again. You return back to the potential. So you keep, as you're taking a walk, converting the rest to motion, to rest, to motion, to rest, to motion. So you have the plot going that way. Okay, because the plot you have is just for one stride. All right, so we can actually from this, we'll have the velocity time graph, obtain several information like the speed at which the person is walking. We know that acceleration at which the person is walking. Velocity time graph always give you the slope to be acceleration. Okay, so and when you do most of these tasks, as we have seen from calculation, we give out, if we're not able to get the output of the maximum energy we put in, we know that some of it has been lost to thermal energy. So most times the energy lost to our system mostly is to thermal energy. So I'd like us to quickly look at this activity before we look at the last part of the class. Okay, let me skip that because we will look at it at the end of the class, okay? This class activity. All right. So the last part of our class, let me rush that before we use the remaining 2 minutes to look at the exercise. We want to establish the relationship between these three terms: temperature, thermal energy, and heat. We use them interchangeably, but they are different, but there's a relationship between them. So we start with the thermal energy and temperature. Thermal energy, as we've seen before, when we looked at energy for friction and all that, is actually the sum of kinetic energy and elastic potential energy of an object. You remember that for friction, when we're describing thermal energy from friction, we saw the spring bond that exists between the two surfaces when you try to move an object off the other one in contact. It breaks that bond, and then that changes, increases the temperature. All right. So we see that the sum of kinetic energy and elastic potential of an object can actually lead to an increase in temperature of a system. So where thermal energy is the sum of the kinetic and potential, temperature is actually the measure of the average energy of the atoms of an object. So the major difference between them is that thermal energy talks about the total energy of the atoms, while temperature is talking about the average. So one speaks about the total sum, but this one is talking about the average. Temperature always refers to average, all right? And we'll have different scale to measure temperature. We'll have this degree Celsius, we'll have the Fahrenheit, and we'll have the Kelvin scale. And we can actually convert each of these values using this formula and this formula, okay? So to take a value from Fahrenheit to degree, it's 5/9 times the value in Fahrenheit minus 32 degrees. Same also happened, the reverse is the case here. To take degree to Fahrenheit, 9/5, the value for degree plus 32. So we have the third scale, which is the Kelvin scale. You can actually convert between Kelvin to degree as well by adding or subtracting 732. Okay, so we'll see the Kelvin scale and the degree scale have the same change in temperature, and this is what we mean. This is 100 and this is 100. The change in the temperature system is the same. Okay, for the Kelvin and Celsius scale. So degree, which is degree Celsius, is acting like the intermediate. It helps to take one from Kelvin, Fahrenheit to degree, then to Kelvin. Okay, using these two equations. So let's take an example. Now, the coldest temperature ever measured on the Earth is minus 29 degrees Fahrenheit in Antarctica. What is this value in degrees Celsius and Kelvin? So we'll be applying those two equations that we saw. So first we convert the temperature for Fahrenheit to degrees Celsius, then to Kelvin. So we use the conversion formula for the Fahrenheit to degree, which is 5/9, the value of the Fahrenheit minus 32. Okay, so we obtain minus 89 degrees Celsius. So to take this to Kelvin, we just added the 273. So we'll have 184 Kelvin. So we can actually convert both, all the values from one to the other. So let's look at the very last of the three components, which is heat. Heat is actually the transfer between two objects, okay? As a result, the transfer of energy between two objects as a result of temperature difference. When there's no temperature difference, heat cannot be transferred. All right, so heat is always flowing from the hotter to the cooler parts and never in the reverse way. Okay, so it does that until the heat system balances. So let's look at raising the water temperature or increasing the heat for the water in the pan. We see these three terms in play here. When we add the thermal energy, addition of thermal energy leads to increase in temperature. And when there is increase in temperature, there will be a flow from the hot to the cold. We see the heat energy with the symbol Q increasing. Okay. So we see at the initial, the thermometer is reading this way, but when when we added the thermal energy, which is the total of kinetic and potential, it led to the increase in temperature, and that increase in temperature actually led to the flow from the hot to the cool region, increasing the total heat in the system. So we'll see the difference between the three terms, okay? And each of them have different symbols. We'll have for thermal, temperature, and then heat, okay? So let's look at the very last information here, which is what actually happens. What is the atomic model for heat? When there's heat transfer, we said that heat goes from hot to cold until the heat balances. How does this happen? So we have a simulated experiment here. The system is insulated, so there's no exchange with the environment. But inside we have the hot part and the cold part. Now, when a system's temperature is high, there is more kinetic energy. So the atoms of that system is moving fast. So you see the vector diagram for the velocity of this atom being higher than that of the atom in the cold system, which is system 2. So that there exists a kind of boundary between the hot and the cold, just like you saw in that, the boundary between the pan and the supply of thermal heat. So the molecules at the edge of the boundary, the molecules come to the edge of the boundary. The one for the heat travels to the edge. This one travels to this side. What happens? The one with the faster speed hits the one that is in the cold region. So it gains energy and it starts moving faster. You see this one loses energy. So this process keeps happening. The energy here is transferred to here. So you see the energy, the flow going from hot to cold until it gets to a stage where the two of them will have the same kinetic energy. At that stage, we say the system is at thermal equilibrium. They have the same temperature. Okay, so we can actually express, in the first case, it was the T1 temperature of the system 1 initial being greater than that of system 2. But at the final, there will be an exchange that will bring about thermal equilibrium and make the system expression to have just one temperature. The whole system will have just one temperature. So T final for 1 is equal to T final for 2, which is equal to the temperature of the system because they are equal. Okay, so the heat energy is basically lost by one system and the other system is gaining. And if they get to thermal equilibrium, this system gains so much that the temperature balances. Okay, so we'll have expression that the heat for Q2, the heat for Q1 is minus, is losing, and Q2 is gaining. Okay, thank you. So that's the last, but I would like you to take the activity before you leave. Okay, so quickly, what is your opinion to the pool I just launched? A runner is moving at a constant speed on the level ground. The runner, is chemical energy from the food he ate. is being transformed to other form of energy. Most of the chemical energy is transformed into what? Okay. Okay, so we have, how many persons have responded? Almost everybody. Remaining, we have 4 persons. Okay, 2 now. Remaining 2 persons to respond, please. What is your opinion? Just put in your opinion. All right. You have just 30 seconds. The 2 persons, where are you guys? Are you not actively in class? Yeah, Osi, I'd like you to wait behind while other leave. I'd like to have a word with you, okay? Are you there? Osia.
Oh, me? Sorry, yes, that's me. Hi.
Okay. Just
I
I'll
have a class after this.
just two minutes, if you don't mind.
Okay, no problem.
Okay. So I'll be ending the class now. Thank you all for responding to the poll. Actually, the answer is C, because we said that what you get when the motion is on, the kinetic energy is like what you get in the end. Why? What you lose to thermal energy is more. Okay, so most of it is going to thermal energy interacting with the environment. So the answer is C. So this question is kind of tricky because we said a runner will convert its potential energy to kinetic, yes, but most, that is the input and output. So if you have your output, which is usually less than your input, some energies are still stored and some are lost to the environment. And the one lost to the environment is the heat, the thermal, which is usually of more percentage. Okay, so take note of that. But the answer to this question is C. In case you see something like this, you just ace it. All right, have A. Okay, thank you so much. Do we have comments, questions? If you have, just send me email, send me a comment on the Zoom or wherever. So if you want to see me today, I'll be in school by 1 o'clock in my office, and I'll stay there for say 30 minutes. So I don't know if you want to come by to settle 1 or 2 things. All right. So Osia, are you there?
Yep.
Can you let me stop sharing first. And
All right, thank